Let's imagine that we're planning a rocket trip, and we've got some object of mass capital M and radius capital R. Maybe this is the Earth or something like that, or maybe some other planet or whatever. Just some body, and we've got a rocket on it with mass of little m and initial velocity v sub I. Now, let's imagine we want to figure out how fast does this thing have to be moving in order to get away from the object. Gravity from the object is going to be pulling the rocket back down. How fast does this thing have to be traveling for it to get away from the body and get way out into space, far, far, far away from space? We can kind of think of this as, imagine we've got an object. If I toss it a little bit, it goes up and comes down. If I toss it faster, it goes up higher, comes down. Toss it faster, goes up higher, comes down. The question is, how fast would I have to throw it, ignoring air resistance and ignoring the ceiling, how fast would I have to throw it so that this thing could actually travel out into space and keep going and make it all the way very, very far away? Say, essentially maybe infinitely far away, but the bottom line is very, very, very far away. Well, we can solve this using conservation of energy. We know initially the rocket will have a kinetic energy of 1/2 little m, the mass of the rocket is little m, v initial squared, so that's v initial squared. The potential energy, when we have two gravitating bodies, two objects with mass, the potential energy is minus g m1, m2 over the distance between them. So the potential energy will be minus big G times the mass of the object times the mass of the rocket divided by r. The distance between them is, say, assuming the object starts at the surface of the whatever this is, planet or whatever, capital R. And then finally, we want this thing to be way out into space. It'll be slowing down as it goes. Let's imagine that when it's very, very far away, it's just stopping. It's just losing all of its velocity. So the final kinetic energy, we'll assume the final velocity is 0, way out, infinitely far away, or very, very far away. The final kinetic will be 0. Final potential, because R now is so big, the final potential will be 0. So we'll use conservation of energy. Total initial energy, which is 1/2 mv initial squared, plus initial potential, minus g m, big M, little m over r, equals the final energy, but the final total energy is just 0. So this equals 0. Well, bringing this to the other side, multiply by 2, divide off the mass of the rocket. Notice the mass of the rocket cancels. Multiply by 2, take the square root. We have the initial velocity is equal to 2gm over r. The root of 2g times the mass of the body divided by the radius of the body. Very, very good. This is what's called the escape velocity. In other words, how fast does the object have to travel in order to escape from this body? Escape meaning like get away, get very, very far away. That's how fast. Now for the Earth, it turns out that this is about 11 kilometers per second. So for the Earth, a rocket has to travel very, very fast. That's why it's so hard to get away from the Earth and get to the moon or something like that. 11 kilometers per second. Now, let's think about what we know about special relativity. Nothing can travel, nothing with mass can travel at the speed of light. So the fastest that any body could travel with mass is less than the speed of light. And the only thing that can travel at the speed of light would be light, or some kind of wave, like gravity waves or something like that. So the fastest that anything can travel would be a velocity of c. So let's just stick c in here and solve for r. What do we get? Well, put c here, square both sides, we get c squared, multiply by r, divide by c squared, and what do we get? We get that r is equal to 2gm over c squared. Now, what does that mean? Well, that means that if we had a body of this mass, m, of this radius, that something could only escape if it traveled at the speed of light. In other words, the only thing that could escape that object would be light. And if it were smaller than that, if this body were smaller than that, the object would have to travel faster than the speed of light to get away from it, and that means nothing can get away from it. So, this is what's called the Schwarzschild Radius. For a given mass, this tells you the radius that a black hole would have if it had that mass. Because an object smaller than that, nothing can get away from that gravitational attraction if it were sitting on the surface of that body. Let's stick some numbers in here. Let's figure out what would be the Schwarzschild radius of the Earth. If the Earth could be compressed down to the size of a black hole, how small would it be? Or how big would it be? Let's figure that out. So for the Earth, with a mass of about 5.97 times 10 to the 24th kilograms, we have 2 gm over c squared. Multiply that out, and we get 8.85 times 10 to the minus 3 meters, about 8.85 millimeters. So about the size of a small marble. In other words, the Earth would have to be compressed down to the size of a small marble to become a black hole. But if that were to happen, then nothing would be able to escape the gravitational pull at the surface and be able to escape. That surface is what we call the event horizon. Because once something gets within that radius, it cannot come out. Nothing can come out. Now, there are some ideas of how energy can come out of a black hole, and Dr. Stephen Hawking came up with an idea of Hawking radiation. That's something that you might look into if you want. I'm afraid we don't have time to go into that at the moment, but there are some ways that energy can come out of a black hole with some very interesting quantum mechanical phenomena. But let me just tell you a couple more things. For the Sun, with a mass of 1.99 times 10 to the 30th kilograms, the Schwarzschild radius would be 2.95 kilometers, about 3 kilometers. So if you could take the entire Sun, compress it down to a sphere of 3 kilometers, it would turn into a black hole. For a person, say an 80 kilogram person, you'd have to compress them down to 1.19 times 10 to the minus 25th meters. So the nucleus of an atom is on the order of 10 to the minus 15th. So this would be 10 to the minus 10th smaller than that. So you don't need to worry about that happening to yourself, I don't think. Well, I'm afraid that's all the time we have left for special relativity and general relativity. Next time, we're going to start looking at a different area of modern physics called quantum mechanics. Special and general relativity deal with some very extreme types of motion. Very fast motion, very high masses. Quantum mechanics deals with very, very small things. Things on the atomic and subatomic level. So, see you next time.